A particle charge q in one dimension in a simple harmonic potential with the angular frequency omega. It is subjected to the time-dependent electric field E of t equal to a exponential of minus t by tau whole square, where a and tau are positive constants, and omega tau much greater than 1. If in the distance was t minus infinity the particle was in the ground state, the probability that it will be in the first excited state as t goes to plus infinity is proportional to what? For finding the probability, transition probability, already the known formula we are going to use. The transition probability from the initial to final state is equal to 1 by Kachikar square minus infinity to t goes to plus infinity to the first existor. So initial to final state in the presence of the interaction, because the time dependent electric field is given. So interaction Hamiltonian initial to final state exponential of minus omega fi, the transition frequency. You can check if it is two level atom. We are giving the time dependent electric field. We want to find the transition probability from ground state to excited state. So this transition frequency omega fi, the separation between the initial and the final state, the frequency separation dot dt dash whole square. Omega fi is nothing but f minus ei by h cut. Final state minus initial state energy divided by h cut. We know the harmonic oscillator ground state energy E naught equal to half h cut by omega. Excited state energy E1 equal to 3 by 2 h cut omega. The separation frequency between the final and initial state E1 minus E0 by h cut. The ground state, excited state minus ground state divided by h cut. After subtracting and dividing by h cut, you will get the omega. So the frequency separation between the ground state and excited state is omega in the harmonic one-dimensional harmonic oscillator. Then we need initial wave function, final wave functions. So we know the ground state wave function for the harmonic oscillator m omega divided by pi h cut whole to the power 1 by 4 exponential of m omega divided by 2h x square. Same first excited state wave function m omega divided by pi h cut whole to the power 1 by 4 square root of 2 m omega divided by h cut x into exponential of minus m omega divided by 2h x square. First we have to find the transition matrix element of the interaction Hamiltonian H dash. So initial state to final state in the presence of the interaction is equal to ground state as well as excited state having same coefficient. If you multiply these two, it will be m omega divided by pi h cut 1 by 4 into plus 1 by 4 1 by 2. Then extra coefficient is here. First excited state, take the out. Then the initial final state wave functions are x into this excited state wave function variables x into exponential of minus m omega divided by 2 h cut x square. Interaction Hamiltonian already we know the interaction Hamiltonian is nothing but minus p dot e. P is a dipole moment operator dot time dependent electric field. So dipole moment operator q into x, the charge time, the separations. Enter the time dependent electric field they are given in the question a exponential minus t by 2 whole square. Substitute this interaction here in the transition matrix element. So minus a q exponential of minus t by tau whole square into x. This is transition interaction Hamiltonian. Now we can simplify the coefficient here. Take the aq constant out. It goes to integration goes to minus infinity to plus infinity. X into x square exponential of minus m omega divided by 2h minus m omega divided by 2h. It will become m omega divided by h cut only. Enter x square dot dx. It's a straightforward gamma integration. We can do. We have the two. So I wrote this exact same earlier here, but exponential of t minus tau t by tau whole square, it is constant. It is independent of the integration. You can, if you want, you can take an out. It's not a problem. You know already the gamma integration use these relations. That means integral of minus infinity plus infinity x square exponential of minus a x square dot dx equal to 1 by 2 square root of pi by a cube. Use this relation. It is simple straightforward. So the transition matrix element is equal to m omega divided by h cut. These are the coefficient front sitting 1 by 2, because we are using this relation 1 by 2 square root of pi by the x square coefficient. Here x square coefficient m omega divided by h cut whole cube. Anyway, this is independent of integration. You can keep it exponential of t by tau as it is. Then after simplifications, you will get square root of h cut divided by 2 omega qa exponential of minus of t by tau whole square. Now this transition matrix element we are going to substitute in the transition probability amplitude. So the transition probability amplitude is equal to 1 by h cut square integral minus infinity to plus infinity square root of h cut by 2 m omega qa, the value of the transition matrix element, the whole value, exponential of minus t by tau whole square. It's an inside integration. Now you can call it as t dash into exponential of minus the omega fi is nothing but frequency separation between the initial and the final state, that is omega into t dash dot dt dash whole square. Now you can take the common thing out. So if you are taking this out, it is whole square already present, so the square root will get cancelled, q square a square will come out. Now keep the integration inside the bracket, square bracket. So this is exponential of minus t dash derivative whole square minus I omega t dash. We are adding and separating this quantity minus I omega tau derivative whole square plus I omega tau derivative whole square. If you are adding subtracting this two quantity, the first three terms it will form exponential of a plus b whole square. Take the minus common out, a square plus b square minus 2ab. So a plus b whole square it will form. This is anyway independent of integration because tau is constant. So you can take this exponential out, that exponential value minus, because the I sitting there. So it will become I square minus omega square tau square 4 by 4 into whole square. This is model square. Actually, this transition property having one more square. It is here. It is whole square. Now, if you are taking this is actually exactly Gaussian gamma integrations or Gaussian integration. If you are taking this answer is square root of pi by a. That means square root of pi by the a coefficient 1 by tau. You have to change the variable, then do the integration. It will give the same answer. Whole square, the front coefficient as it is. So exponential of minus omega square tau square by 4 whole square. So the front coefficient, everything is constants. Pi square, q square, a square, tau, the frequency separation, m2, h cut, and big c dash. This is a constant. If you see the exponential term, if you are it's already power of power. So you can multiply these two. If you multiply these two, it will become exponential of minus omega square tau square divided by 2. So in the question number, given option is 1.